In this video, we'll be discussing material from section 2.1 on increasing, decreasing, and piecewise functions and their applications. Here are our learning objectives. So let's jump right into some definitions. We say if a graph rises from left to right, we say it is increasing. If a graph drops from left to right, we say it's decreasing. And if a graph stays the same from left to right, it's said to be constant. So here's some examples. An increasing graph, when we read it from left to right, you notice that it goes sort of upwards. And if we want to think about that in symbols, then anytime that we have inputs A and B, where A is less than B, then their outputs are also in that order, where the output of A is less than the output of B. Now, a function is said to be decreasing if the opposite happens. For any A less than B that are our inputs, the output of A is actually greater than the output of B. And that looks like something kind of having a downward trend on our graph. Now, a function is said to be constant if for any A and B, we have f of A equals B. So you see it's a horizontal line, which we already know are called constant functions. So we'll ask you to do something like this. Determine the intervals on which the function is increasing, decreasing, or constant. And the intervals are all intervals in x. Okay, so looking at this function, I see it's increasing from here at -4 as my x value, all the way up to here where I have 1 as my x value. So I'll say we're increasing from -4 to 1. Now we always use parentheses here. I'll erase some of these notes, clean it up. We always use parentheses here because it's not increasing at the endpoint -4, just beyond the endpoint -4. Decreasing. Now we can see it's decreasing from right in here, which is at 2, until right in here, which is at 4. So we are decreasing, again, open interval, from 2 to 4. Now when we want to look at constant, well, we are constant right here to right here, which is from 1 to 2. 1, 2. Again, parentheses, not brackets, because we don't include the endpoints when we're talking about increasing, decreasing, or constant. But this will be on your homework, so please reach out if you have questions. Now we're getting into relative max and relative min. So suppose we have a function for which the output exists for a given input C. Now, bear with me through these definitions. It's a lot easier to understand looking at a picture than it is when reading through these. But we say f of C is a relative maximum if there exists an open interval, which means parentheses, not brackets, I, containing C, such that f of C is greater than f of x for all x in the interval I, where x is not equal to C. Wow, what symbolism we have there. Okay, definition of relative minimum. F of C is a relative minimum if there exists an open interval I containing C, such that f of C is less than f of x for all x in I, where x does not equal C. All that's to say, when we look at these pictures, if I were to zoom in right here on the graph, then I would see I have one point that is taller than all the rest, which means that is my relative max. Okay. Whereas in here, if I were to zoom in on this area, I'd see I have one point that's lower than all the rest. So that's a relative min. And this problem actually has two relative mins because they're both right there. Again, you can zoom in on that piece of the function. I can't zoom in on this piece of the function and have a clear point that's bigger than the rest of them. So using the graph to determine any relative max maxima or minima of the function. So right here, I have my maxima, right? It's kind of at the top of my hill, therefore it's the max. So we say I should say relative max. The relative max equals 5.926. It equals my y value, and it is at x equals negative 1.667. Okay, so my relative max is the value 5.926, and it is at x equals negative 1.667. Similarly, for relative min, that is at, the relative min is 0, right? It lands right here on the 0, and it is at x equals 5, okay? So typically that's how the questions will be asked. You'll be asked, what is the relative min? Well, it's 0. Where is it the relative min is x equals 5. Now, determine any relative maxima, minima of the function and the intervals in which the function is increasing, decreasing, or constant, all using a graphing calculator. Okay, so let's jump over to the calculator. And on the calculator, we're going to go to y equals. And we're going to plug in that function that we had, which was 16x divided by, put in parentheses, x squared, try again, 16x divided by x squared, there we go, plus 4. Just going to double check my slides. Yeah, x squared plus 4. We hit enter and we go to the graph. All right. Interesting looking graph. It's hard to tell without zooming in, getting really precise on where is that kind of valley happening, my lowest point, where is my highest point happening? Because clearly we're decreasing for a little bit, then we start shooting up and increasing, then we decrease again. So it'd be nice to know exactly where that happens. And to know that, we're going to say second, calculate. We're going to scroll down to minimum. Now it asks me, well, where's the left bound of my minimum? So I'm going to scroll to the left of where I can clearly see a minimum. I hit enter. And then I scroll with my button over to the right until I'm clearly to the right of the minimum. I hit enter again, and I hit enter one more time. And it clearly found the minimum at negative 1.99998. We're going to assume that's negative 2. And y equals negative 4. So that's x equals negative 2, y equals negative 4. So now I can clear that, and I can say second, calculate, and I can go to my maximum. And I can mark, well, where is the left bound of my maximum? And I just have to make sure I'm to the left of my max. And then I'm going to scroll over and make sure I'm to the right of my max. I hit enter. I hit enter one more time. And it marks it exactly at 2. So x equals negative 2 was our minimum. X equals positive 2 is our maximum. Then you could tell that we're decreasing from negative infinity up to that negative 2 value where that minimum sits. And then we're increasing from negative 2 to 2. We're decreasing again beyond that. Okay. So let's write all of that down, switching back to our slides. So the min, gotta turn my pen on. The min was at x equals negative 2, and it was, you know what, I would write it this way. The min was negative 4, and it was at x equals negative 2. And the max was 4, and it was at x equals 2. Remember, it kind of did one of these. That's terrible with that axes. Go ahead. I would suggest having the graph in front of you while looking at this right now. But then we write down our decreasing interval was from negative infinity until negative 2, union, and then we started decreasing again from 2 to infinity. Now we were increasing from negative 2 to 2. Okay, so that middle section we were increasing and everywhere else we were decreasing, right? And it helped to know our maxes and mins ahead of time. So moving on, we have an example about car distance. We want to try to express a distance as a function. So we have two nurses, Chiara and Matthias, and they drive away from a hospital at right angles to each other. Chiara's speed is 35 and Matthias' speed is 40. Express the distance between the cars as a function of time. So this is kind of the picture of what we're looking at. Matthias' distance is given there and Chiara's distance is given there. So, and they're driving away from each other at a right angle. And you can kind of assume where we're going with this using Pythagorean theorem. Okay. So remember, distance is rate times time. So the distance for Matthias is exactly given by 40 as our rate times the time. And Chiara's distance is exactly 35 as the rate times the time. So if I'm thinking about our distance formula, let's think about this d of t, along this hypotenuse. And let's try to write this down as Pythagorean's theorem. So what that means is this is my side C, this is my side A, and this is my side B. And as a recap, we have a squared plus b squared equals c squared. So that's where I'm going with this d of t squared is actually 40t squared plus 35t squared. But I wouldn't want my d of t to have a square on it, so we square root, and we get that our distance is the square root of 40t squared, that needs to be in parentheses, plus 35t squared. And that is it. We could simplify from here a little bit more, squaring the 40 and the 35. Maybe we'll go ahead and do that actually, see what happens. So let's see, 40 squared, I believe is 1600. And then it's t squared plus now 35 squared. That is 1225t squared. And notice that's a 6 and that's 1600. There we go. So 1225 plus 1600. We get the square root of 2825t squared. Well, the square root of 2825 is, let's see, 1 second, 2825. Here we go, 53.15 t. Because notice the square root and the t squared kind of cancel. I did the square root of 2825, we get 53.15 t. So our distance overall simplifies all the way down 53.15 t. Okay, moving on to another example. Here we have Rick's lumberyard has 580 yards of fencing with which to enclose a rectangular area. If the enclosed area is x yards long, express the area as a function of its length. So let's draw a picture. Here's our length x. And we know that the total here is 580. So let's suppose that I'm trying to decide. Let's draw our picture a little bit more. We know if we have a length, which this one's our x, and we have a width, we know the other side is also width, and the other side is also the same length, right? Just given a rectangle. We know area of a rectangle is length times width. We know that the perimeter is 2 times our length plus 2 times our width. And that is what equals 580. Okay, so this, I need to figure out, well, how am I going to represent the width using that 580 number? Well, in terms of x, right? So I know that my length equals x. So this is really 2x plus 2w equals 580. And bear with me here, we're just going to solve for w, and then we'll know what our width is in terms of our length x. So I'm going to subtract 2x from both sides, and I get 2w equals 580 minus 2x. Divide by 2 on both sides, and I get w is, and 580 divided by 2 is, 290 minus x. Okay, so then that means that each of these widths I could replace with w equals 290 minus x. Well, that means I can go back to my area formula, and I know area is my length x times 290 minus x. And all of a sudden, we've expressed the area as a function of that length. That was what they asked for. Now, another example. And let me note that each of these are, in fact, on your homework. So it's important that we're going over them now. So, third example. From a 24 by 24 centimeter piece of cardboard, square corners are cut out so that these sides can be folded up to make a box. Express the volume of the box as a function of the side x in centimeters of the cutout square. Using the graph of the function shown, determine the dimensions that yield the maximum volume. So to solve this problem, to start off, remember that we need to use the volume formula. And that is V equals length times width times height. We also want to remember that the length of this cardboard box was 24 inches. And that it's a square, so this side is also 24 inches. So remember, we are asked to express the volume of the box as a function of the side x. Okay, so we want to get that formula down to only x values. Well, notice once I take this x value here, this kind of side length of x, and I flip it up to make a box, my height exactly becomes x. Then my length and my width, which are the same because this is a square, is 24 minus 2x, right? Because I've taken off an x piece here and an x piece here, and the full length was 24, so as I remove those two, I get 24 minus 2x. That means my volume is my length, which is 24 minus 2x, my width, which is 24 minus 2x, and my height, which is just x. That is our volume function. Now, we want to use the graph of the function to determine the dimensions that yield a maximum volume. So we're going to graph this volume function and see where the max is at. So let's jump back to our graphing calculator. Doing something like this on Desmos is actually much easier because we can actually see the window a little bit easier. It's easier to manipulate. This is all possible on a TI-84 as well, but you'll find Desmos is a little friendlier. So let's jump to Desmos for a minute. We are going to graph 24 minus 2x times 24 minus 2x times x. And notice I don't have to solve this or simplify it. I can just type it in simply like this. And I'll scroll out, zoom out a little bit. We can move around. Okay, we can see somewhere along here we have a maximum. Just easier to navigate. Okay, we see our maximum happens right here at 4, 1024. The other nice thing about Desmos is you can just click on a maximum to see it. We don't have to go through the calculator and hit graph maximum. So 4, 1024. Let's go back to our slides and we'll see. To answer the question here, we had the point 4, 1024 as our max point. That means that the max volume is 1024, and the dimension would be height, which is x equals 4. And then we actually have to go back for the other two. If you remember, our length and our width is 24 minus 2x, and our x value is 4. So this is 24 minus 2 times 4, which is 16. So the largest box we can get is 16 by 16 by 4. And that max volume will be 1024. Okay, moving on to some piecewise function. Functions are called piecewise when we're using different output formulas for different parts of our input domain. Okay, so essentially when I see this, I think, okay, for all x values where my x is less than -2, I'm going to evaluate it using this function. For any x values between -2 and 3, I'll evaluate it using this function. And for any x values greater than 3, I'll evaluate it using x squared. So that's how we think about different piecewise functions. Now let's see some examples working with them. So for this function, let's find all these different f values. So for f of -5, for that one, I'm looking, okay, my x is -5, which means I had a glitch there, -5. That means that I want to think about, okay, which of these values does -5 fall in? Well, it clearly falls in the first one, right? -5 is less than -2. So that means I want to be using x plus 1 at this case. So it'd be -5 plus 1. And that gives -4. I'm going to write it to the right, give myself some more space here. -4. Okay, now let's think about f of -3. Hello, 3. Well, -3 falls also less than -2, so we're going to use that first line again. X plus 1. So that becomes -3 plus 1, which is -2. Now if I think of f of 0, well, f of 0 is my x value, and 0 is between -2 and 3, which means I'm using this one. No x values to plug into, I just simply write it down. Now we're thinking about f of 3. So my x value is 3 here. So I got to think about, okay, where does x equal 3 belong? Well, x equals 3. I see a 3 in my middle line and my bottom line, but the or equals to is right here in the middle line. So f of 3 is also 5. Now we write down what is f of 4. Well, clearly 4 is greater than 3, so I'm going to use my last line here. And I evaluate 4, and I'm going to evaluate it using the function given for x greater than 3. So that's 4 squared, which equals 16. Similarly, for f of 10, I think, okay, my x value is 10. 10 falls greater than 3, which means I need to use x squared to evaluate it. That gives me 10 squared, which is 100. So piecewise functions just say, hey, for different values of x, you're going to plug it into different functions. Now let's talk about what it takes to actually graph these functions. What this means is, okay, I'm going to do something for every x value that's less than 3 and something else for x values greater than or equal to 3. So in theory, I should see a change in my function somewhere around this dotted line. And to the left of that line, I'm going to do my top function, and to the right of the line, I do my bottom function. So let's go ahead and graph that top function. If I have this is of course a line in the form mx plus b. So my b value is 3, which means I'll start there. And I just need one more point, so I'm going to use the slope. So it's rise over run, I rise 1 and I run 3. I rise 1 and I run 1, 2, 3. And I'm going to go ahead and draw my straight line, and I'm going to only draw it to the left of that given line. Now, I drew my 2 points. However, the points make it actually a little bit confusing in the long run because, oh no, well, let me just draw it again real quick. 1 second. I accidentally erased my line. It goes all the way down like this. So right here, we actually want to have an open circle because I don't have an or equals to here. That's attached to my lower line. So please believe me that that is an open circle in there. And then I have the line going to the left. Now for this guy, this is all happening to the right. So I'm going to graph it, but then I'm going to erase anything that's happening to the left of that x equals 3 line. So here my m is -1, my m is -1, and my b is 0, which means this guy really starts at 0, 0, and does a down 1 over 1 to draw the line. Which means if I think about it, it's coming down like this. Right through the corners best I can. However, let me draw it in 2 pieces. So it's kind of coming down like this, and it's going up. Why'd you do that? Computer, come on now. Go back. There we go. And it's coming down like this. Keeps going. So that's what that full line would look like in theory, only I want to erase everything going on to the left of 3, right? X equals 3, because that isn't picked up until I'm to the right of this, right? So all these x values are where that guy applies. And I want to have a closed circle on this guy since I'm actually or equals to here. So it's 2 lines, and I do one line up to x equals 3, and I do a different line beyond x equals 3. That's what we're looking at here. So let's try another one. The graph of the function defined as f of x is -2x plus 1. So this is, again, mx plus b. How we want to think about it, we're doing one thing on the left-hand side of the graph and another thing on the right-hand side of the graph. So our b value is a plus 1, so we're sitting right there. And we have a -2 over 1 slope. -2 over 1, -2 over 1. I'm just going to draw a few in the other direction as well. Up 2 over 1, up 2 over 1. So this line is looking something like this. And I won't even draw it to the right. Okay, and I'm going to leave it open here because I don't have an or equals to with my first line. I have it on the second line. And I don't really need these extra dots, but they were just to help me draw the line. So I've drawn my top line, -2x plus 1. I suppose I could throw an arrow on there, but that kind of thing. Now I want to graph the line x. So this is, my slope is 1 and my b value is 0. So I'm starting at the origin with this one, and I go up 1 over 1, up 1 over 1. I'll draw a few points out here. We see this shoots off right like this. And just to clarify, this circle is open and the other one is closed. Okay. But this is what our piecewise function looks like here. To the left of our y-axis, because that's where x is less than 0, I'm using -2x plus 1. And to the right of the axis, I'm using just y equals x. And it's okay that there's a disconnect between the two. It's not a big deal. Sometimes they connect right in here, sometimes they don't. All right, something else that we might see are these kinds of functions. And it might be easier to see it if we graph it, but I'm going to go ahead and walk you through actually doing a little bit of simplifying and then graphing. So you might believe me that if we take this first one and simplify it a little bit, and we have x squared minus 1 over x minus 1. If I factor that top, I actually get, x minus 1, x plus 1. So for everywhere where x minus 1 is non-zero, I can do that and cancel. And I'm just looking at x plus 1. So this top row, I'm actually not even going to think about it like that. I'm going to think about it as x plus 1 because that's the simplified version of it. And that's much easier to think about. So on top I have x plus 1, and on bottom I have 4. So basically everywhere where x is not 1, we're doing x plus 1. And everywhere where it is 1, it must be 4. So we're going to start with that second line, which means when x equals 1, we must have 4. So when x equals 1, I must have the y value 4. Okay, but everywhere else we have x plus 1. So let's draw that line. I start with a plus 1 right here. My slope is 1, so I go up 1 over 1, up 1 over 1, up 1 over 1. Kind of like this. So here's what this line looks like. And it's all x values except right in here. You know what? Let me draw it in 2. I go down like this. And I go up like this. Whoop. And right in the middle here, if I can carefully delete my dot, I have a big open, or not. I have a big open circle right in the middle there. That tells me, hey, we're going to skip over x equals 1 on this line, and it's actually going to be evaluated up here. So if I were asked, well, what is, let's say, f of 0 in this case? Well, f of 0 is clearly just 1. I read it off of this point right here. I could say f of 2. Well, that again, I read off the line is just 3. But if I say, well, what is f of 1? Well, that is actually 4. I don't look at the line. I don't try to call it 2. It's actually evaluated up here at 4. Okay? That's all. That's how we work with this kind. Now let's say that you're given a graph and we need to write down an equation for the function. And in this case, we're also going to be thinking about the domain and range of the function. So we're given this almost step-looking function where it's evaluated for a while at 2, and we have an open circle, we have a dot somewhere in the middle, and we have another open circle at the bottom, and it continues on at -4. So we want to write this down. F of x equals, and I count 1, 2, 3 things happening. So we're going to have 3 lines here. So for the first line, from everywhere where x is less than 1, we have a constant function at 2. So that's what that first line looks like. My constant function 2 applies for everywhere where x is less than 1. At x equals 1, I have the function value 1. That's this point right here. And then for everywhere where x is greater than 1, I have the constant function -4. And there you have it. We actually have just written down the equation, the function, this piecewise function represented by the graph. And so if we want to think about the domain, well, I'm going from -infinity to 1 here, and then 1 is defined. And then I'm going from 1 all the way up to positive infinity. So my domain goes all the way from -infinity to positive infinity. And my range, remember, is all of the y values covered by this function. And so it's actually just a set of 3 numbers. I only have 3 y values anywhere on this graph. The first one is 2. all my function sits on 2 up to x equals 1. I also have something at 1 right in there. And then lastly, I have -4. So my range is a set of 3 numbers, 2, 1, and -4. All right, so let's try it again. So determine the domain and range of this piecewise function shown in the graph, and then write the equation of the function. Notice it's kind of easier to do it the other way around, in my opinion. So we want to think about a piecewise function, f of x equals. Now again, I see 1, 2, 3 things happening, so I think we're going to have another 3-liner here. So from x equals 9 till x equals 3, -3, 1, 2, yeah, -3, nope, -2. From x equals -9 to -2, we have this first line. So that's what's going to go here. We have -9 less than or equal to x less than or equal to -2. And we're doing something that we'll fill in here in a second with this first line. Now from 2 to 0, -2, excuse me, to 0, we have that constant function at the bottom. So we have something from -2 to 0. Oops. Now, I've kind of been glazing over this, but that -2 in that first line stopped at an open circle, so I shouldn't have had the or equals 2. The other two have closed circles, so we're good to have the or equals 2s. We'll fill in the constant function in a second. And for our third line, we're looking at something from 0 all the way up until 5. So 0, open circle, closed circle gives us an or equals 2 up to 5. So there I've just broken up my domain into its 3 pieces, and I see my 3 lines. So now I just got to fill in, well, what is the function, the formula, the equation for that line? What is the equation for that line? And what is the equation for the third line? Once we write those down, we're good to go. So hopefully you agree with the first line. You can see that the slope is 1, m equals 1 there. And if I kept going, which is usually the easiest way to think about it, I would have landed on the y-axis at 12, which means my first function is x plus 12, right? It would be 1x for my slope, 1, but really we're just looking at x plus 12. Now my second one is a constant function at -5, 6, 7, -8. So that's just a single number at -8. And lastly, I see my y-intercept here. B is -9. And this has a slope of rise 1, 2, 3 over 1. So my slope there is 3. 1, 2, 3, yeah, 3 over 1. So my last one is 3x minus 9. There you have it. That is our piecewise function written down. So it's a matter of breaking up the x values into their separate pieces and then writing down the equations of the different lines. Now, when we think about our domain, well, we span everything from -9 up to 5. And those are included since we have black dots on the ends there. And our range covers everywhere from, I think up here at 9 is our highest value. And everything is hit at least once down to -9. So we are actually covered from -9 to 9. Neither one ends on a closed dot, which means that we use parentheses here. And that's it for this example, our domain and range. Now, lastly, a quick thing to note, this bracket x with the extra lines is what we call a greatest integer function, and it is the greatest integer less than or equal to x. So you basically always want to take off the decimal part and round down, though if it's a negative, taking off the decimal part really means rounding. Rounding down increases the number itself. So something like 3.6 gets sent to 3, something like 10.25 gets sent to 10, something like negative 5.4 gets sent to negative 6. So always go with the number less than the input. And you'll see an example working with this function on the homework. It comes with an extra video there, so I think you guys will be in good shape. As always, reach out if you have any questions.